Hey guys, Ms. Marusik here, and in this video we're going to talk about titration calculations involving a strong acid combined with a strong base. Now, to do a strong acid, strong base titration calculation, I like to use the acronym of NDS. N for net ionic, D for dilution, and S for stoichiometry. Now, let's talk about each of those in a little more detail. Net ionic, what I would want to do first is figure out for the strong acid and the strong base what the overall net ionic equation would be. The reason why I want to do that is because I need to pay careful attention to where I have hydrogen ions and hydroxide ions, because eventually I want to calculate pH. And so by narrowing down the reaction to just the net ionic, I can focus my attention on just those ions. So then the next step is a dilution. So here's the information you're going to be given typically. You are going to be told for a particular point in your titration what volume and molarity of acid you have and what volume and molarity of base that you have that you're combining together. And the goal is to eventually figure out what the pH is. However, when I add those two solutions together, what happens is that the volumes add together. And unfortunately, when that volume of the overall solution becomes greater, the molarity of both the acid and the base decrease. They get diluted. And so I have to figure out, once I've combined them together, what is the new molarity for both the acid and the base. And so we're going to have to do a Voom calculation for both the acid and the base. So we're going to have to do two of these V1M1 equals V2M2 calculations. The third step would be stoichiometry. Once I know how much of the acid and the base that I have, I want to figure out which one is in excess. And so what I'll need to do is figure out who my limiting reactant is. I know that will get all used up. And then I can use the excess to figure out the pH. However, rather than doing our traditional stoichiometry dimensional analysis setup here, we're going to actually do this stoichiometry using a non-equilibrium rice table. I like to call it a modified rice table because I know I'm not doing a traditional equilibrium where I'm going to have a little bit of everything left at the end. With a modified rice table, you might be using all of something up. And so using that kind of setup will save us a little bit of time rather than trying to do a whole bunch of dimensional analysis. So within this whole entire process, we're going to be really focused on what all of these various molarities, these concentrations would be. So have you figured out the pun yet here? It's time to do titration calculations, and we need concentration. Oh, that's a terrible pun. You're like, please, Marusik, don't do that. Okay. Now I will tell you this. Eventually, in another video, we will talk about combining a strong with a weak, either a strong acid with a weak base or a weak acid with a strong base. So we will have an extra step to this acronym when we get to those problems. But for now, I want you to remember the acronym NDS, net ionic, dilution, and then some stoichiometry. So with that said, let's go ahead and start to see how these calculations would work on the next page. And so we're going to start off here, given a titration of 60.0 milliliters of 0.1 molar hydrochloric acid with 0.2 molar sodium hydroxide. And the first thing it has us do is actually the first step in the NDS process. It has us to figure out what the net ionic equation would be. And so what I did first is I did my regular double replacement reaction between HCl and NaOH, and I figured out that when I did my double replacement that made water and sodium chloride. And I know sodium chloride is aqueous because it's a group 1 ionic salt. And so then anything that was AQ and was a strong acid or strong base would completely split apart into ions. So here the HCl will split up and the NaOH will split up. Again, they both split up because they're both strong. Our water, liquid water, we would leave together. The NaCl, being a soluble ionic, would completely split apart as well. And so then you notice that we have some spectator ions. Now, I didn't cross them out, but you notice we have the chloride ion from side to side and the sodium ion from side to side. So those spectator ions are always going to be present as this titration is occurring, but they themselves aren't going to be participating in the titration. What is going to be participating in the titration is the hydrogen ion and the hydroxide ion coming together to make water. So this is our net ionic equation. And I've got a secret for y'all. Anytime you have a strong acid with a strong base, this is always going to be your net ionic of that particular type of combination. Now, when we do our weak with strong on another day, those net ionics get a little more complicated. And so we'll talk about those in a later video. So on this next step of the problem, they want us to determine the volume of NaOH it would take to fully titrate the HCl. Basically, what they're asking us to do is to figure out what volume would I need of the sodium hydroxide in order to reach the equivalence point where the HCl and the NaOH were fully canceling each other out. Now, this is different than the stoichiometry step that we're going to see here in a little bit within the NDS calculation. This is just asking us to do a regular stoichiometry like we've always done, where we say, hey, if I have 60 milliliters of this 0.1 molar HCl, what volume of this 0.2 molarity NaOH would I need to use in order to figure out where that equivalence point is at? And so what I did here is I said, well, hey, how many milliliters of NaOH would equal 0.06 liters of HCl? I converted my hydrochloric volume into liters. I then used my molarity here, the 0.1 molar, to say, hey, if it's 0.1 molar, that's 0.1 moles for every 1 liter of HCl. So I used the molarity as a conversion factor. I then said, hey, for every 1 mole of HCl, we need 1 mole of NaOH. That's the stoichiometry ratio between the coefficients from my reaction. And then I said, hey, using this molarity of 0.2 molarity, that would be 0.2 moles of NaOH for every 1 liter of that solution. That would get me 0.03 liters of NaOH that I need, which would be 30 milliliters of NaOH. What that means is that I would reach the equivalence point once I reach 30 milliliters of sodium hydroxide added. Now, one of the steps that we'll see later on is that 30 milliliters of sodium hydroxide. So if I've already done this calculation, I know where that equivalence point should be. You don't have to do this step beforehand, but if you have done it, then it helps make one of our later calculations a little bit easier. So we'll revisit that here after a while. The next part of this problem wants us to determine the pH of our solution before we add any NaOH whatsoever. This is actually what we've already done on a previous day. What we want to do is we want to figure out the pH of this 60 milliliter 0.1 molar hydrochloric acid solution. We are trying to figure out the pH of a strong acid. So think about how we've done that in the past. So this is going to look really familiar here. Let me put this all up. So what I would have done is I would have said, well, hey, that HCl, before I add any NaOH to it, would break up into hydrogen ions and chloride ions. And it's a one-way arrow because it's strong. Now, you could have shown this with adding water and then end up forming hydronium. You would have gotten the same thing here, so kind of a take your pick on how you want to show that. I just showed the simplified one here since I know this is a strong acid. I don't need to show that water here. If I had 0.1 molarity of the HCl to begin with, that's going to all go away because this is strong, and it's going to all turn over into hydrogen ions and chloride ions. So I see I have 0.1 molarity of the hydrogen ions. So then I can take the negative log of that value and end up solving my pH. So you can see this is just like we've done on a previous video, no different. And so my initial pH value before I put any sodium hydroxide into that analyte, just the pure starting analyte by itself, would be 1. And the ions currently present in the analyte would be hydrogen ions and chloride ions. So now here's where we're going to start to slowly add some NaOH. So to that 60 milliliters of 0.1 molar HCl, I'm going to start to add a little bit of sodium hydroxide. Here I'm going to start off with adding just 10 milliliters. Here is where I want to think through my NDS, net ionic dilution stoichiometry. I'm starting that titration process of combining things together. I'm combining a strong acid and a strong base, so I need to think through NDS. So let's kind of start talking about that. Now, I'm going to go ahead and put up some work here, but we're going to discuss through it here. So what I did first is I actually went and figured out what would be my new total volume. Okay, I have 10 milliliters of sodium hydroxide, but I know I'm putting with it 60 milliliters of that original HCl that would have already been in that container. So I'm going to have 70 milliliters here, and we're going to use that here in a moment. So let's do NDS. N, net ionic, strong but strong. So I wrote H plus OH yields H2O. That's my net ionic for this step. Okay, so that's the N. D, I want to next do a dilution. I know that the molarity of NaOH was originally 0.2 if it's in 10 milliliters. Up above, they gave us that the 60 milliliters of hydrochloric had a molarity of 0.1. But those aren't the molarities when I now have 70 milliliters of total solution. So I need to do a VUM calculation for both of these to figure out what's happening. Now, you notice that I did this for H and OH. Now, let's think about why for a minute. The HCl, when it dissociates, gives me hydrogen ions. So if I had HCl at 0.1, then I'm going to have hydrogen also at 0.1. So notice for the hydrogen, when I set up my VUM, I said, hey, the original 60 milliliters had a hydrogen ion concentration of 0.1. But now I want to figure out that molarity when I have 70 milliliters of total solution. And what we should see is that molarity decreases a little bit as that volume goes up. And what I did is I put my calculation answer down here. That gets an answer of 0.0857 molarity for that hydrogen ion now in the 70 milliliters. I want to do the same thing for the hydroxide. Now, sodium hydroxide, when it dissociates, gives me 1 hydroxide, and so therefore it should have the same molarity as the NaOH. So notice for the OH, I said I had originally 10 milliliters, that was the volume they gave me here, of 0.2 molar OH. Now, I will warn you, if you had had 2 hydroxides here, then this molarity would have needed to be doubled. Remember, we did that when we did our strong acid and base calculations. If this releases 2 hydroxides, then this molarity gets doubled. So the only reason that this was the same is because it was a 1-to-1 ratio. However, I want to figure out what the molarity would be at the new 70 milliliter total. And so again, I do a VUM calculation, and that gets me a new hydroxide concentration of 0.0286 molarity. So now I have the molarity of H and OH. So I've done the N, net ionic. I've done the D, dilution. The next step would be stoichiometry. So this is where I'm going to kind of think through a modified Rice table. I have my initial concentrations, and I already had my reaction, so I already have the R and the I. And what I want to do is I want to think about which of these concentrations would limit my process. And if I notice, I have less molarity of hydroxide ions than I do of hydrogen ions. And it's a 1-to-1 ratio, so I should react equal molarities of the two. So what that means is that having less hydroxide means that it is the limiting reactant. So I put LR here to remind me that this was my limiting, okay? So what that means is that this hydroxide is going to get all used up. in my process. Remember, the limiting reactant always gets used up in the process. For the hydrogen, since these are in a 1-to-1 ratio, I'm going to also use 0.0286 molarity of it. And so when I subtract those, that gets me an ending concentration for the hydrogen ion of 0.0571 molarity. Again, you notice it's a rice, it's just not an equilibrium rice. I'm just assuming that I'm using up all of my limiting reactant, and for my excess, I'll have some remaining. Okay, so again, not quite an equilibrium rice, but I'm still thinking through that rice setup. Okay, so now look what I have. I have hydrogen ion concentration. Can I calculate a pH from hydrogen ion concentration? Yeah, you betcha I can. And so look, here we go. I'm going to take the negative log of that 0.0571, and that gets me a pH value of 1.243. Now, let's talk about the ions present in the solution for a minute. I'm actually going to go back up for a moment to my reaction up here, and I'm actually going to look at the complete ionic. When I start adding the two of these together, ion-wise, I should always have some sodium and some chloride ions in my solution. Why? They're spectators, so they're always, chilling out in that solution. They're always going to be in there. Now, for the hydrogen and the hydroxide, I may have one but not the other, or I might not have either. So we're going to talk about that as we go through. So here on this problem, I know I'm going to have the sodium and the chloride ions. Why? Because they're spectators. They're always in there. But the hydroxide's going to all get used up. So when I'm thinking about the ions present in my final solution, I'm going to have sodium ions, chloride ions, and hydrogen ions. No hydroxide. Why? That was my limiting reactant and it would all get used up. All right, let's do another one. Here on this next one, we want to determine the pH when 15 milliliters of 0.2 molar NaOH has been added. So now we've added a little bit more of that sodium hydroxide than we did before. Instead of adding just 10, now I'm adding 15. So again, I'm like, okay, this is a step in a titration process between a strong acid and a strong base. I need to think through NDS. And so here we go. First thing I would do, write my net ionic. You notice it hasn't changed. It's still H and OH ions making water, right? So that's the N. D, dilution. So first, let's talk about the hydrogen ion. Again, originally, according to the first point in the problem, I had 60 milliliters of 0.1 molar HCl to begin with. That has one hydrogen in it. But now I'm going to have 15 plus 60 milliliters of total solution. So I'm going to have 75 milliliters total. So I need to figure out what the molarity of the hydrogen would be in that 75 milliliters. And so I would solve my VUM, and that gets a concentration for H of 0.08 molarity. So then I do the same thing for hydroxide. Again, I had 15 milliliters of that hydroxide solution. Since there was only one OH in here, this molarity is also the molarity of the OH. If I had two OHs, I would have had to double it, but I didn't have that. And so then I want to figure out, well, what would the molarity be at 75 milliliters? And so again, I solve my VUM, and that gets a molarity of 0.04. Okay, who do I have less of? These are in a 1-to-1 ratio. Well, I have less hydroxide, so that means it's my limiting reactant. I'm going to use all of that up. But in using all of that up, I would also use 0.04 molarity of the hydrogen ion. What does that leave me with? Well, that leaves me with 0.04 molarity of the hydrogen. Okay, so now we've done the N, the net ionic, the D, the dilution, the S, the stoichiometry, and now I want to solve pH. And I'm like, well, hello, I have the molarity of the hydrogen ion. So let's negative log that sucker. Right? And if I negative log 0.04, that gets a pH of 1.398. Now notice what's been happening. We started at a pH of 1. We then went to 1.243. Now we're at 1.398. Do you see how we're starting to inch up? we're starting to add more and more of that base, utilizing up that hydrogen ion. And so we start to see our pH start to increase. Now, as far as the ions present in the solution, we're going to see the same ions we saw on the previous problem. We're still going to have sodium and chloride ions. Those are the spectators. They're still going to be in there. Hydrogen was in excess, so I'll still have that in the solution, but no hydroxide. Okay, that was the limiting. I used all of it up. All right, let's go ahead and turn the page and look at our next calculation. Here, we wanted to determine the pH when 30 milliliters of 0.2 molar NaOH has been added. And I'm like, 30 milliliters, that sounds really familiar. And we're going to talk about why that sounds familiar here in just a second. Let's say I didn't know anything about this step, and I'm like, oh, what's another step in a titration between a strong and a strong? Guess the acronym I'm going to use. Oh, yeah. We know it. Let's start off with our net ionic. H plus OH yields H2O. We know that that's going to be it. So there's my net ionic. Next, I want to do my dilution. For the hydrogen, 60 milliliters of 0.1 is where we started. But look, now we're going to have this 30 milliliters plus the 60 originally. So now my total solution is going to be 90 milliliters. Okay, so I want to figure out that molarity at 90 milliliters. When I solve that, that gets 0.0667 molarity. I then do the same thing for hydroxide. Here I had 30 milliliters of 0.2 molar NaOH. There was only one OH in there, so the molarity is the same. And I want to figure out what the molarity would be, though, at 90 milliliters. And so again, I solve my for the X, and I see that that gets 0.0667 molarity. And I'm like, hey, wait a minute. I have the same molarity of each of these. And so if I use all of this up, it'll use all of this up, and I end with none at the end. And I'm like, what in the world? How can I have none left at that point? Think back to our previous page for a moment. Do y'all remember back here where we did this stoichiometry? And we said for our 60 milliliters of HCl, to cancel it out perfectly and reach the equivalence point, I would need 30 milliliters of NaOH, right? Did you notice what we added on this problem? There's where we added that 30 milliliters of NaOH. So the reason why H and OH cancel out is that we have now reached our equivalence point. Perfectly balanced, canceled out stoichiometrically. And so what that means is that I have a pH of 7. Now let's think about our ions present for a moment. We know we're going to have our spectator ions. We know there's sodium and chloride floating around in that solution. But think what else happens. There's going to be no H or OH. Why? They've canceled each other out. So what happens is at that equilibrium moment, there's no extra H or OH in the solution. The only H or OH, the little bit that might be present, is because of the water itself doing its autoionization. And so, yeah, there's an itty bitty little bit in there, but there's no significant amount, which is why we say we're at the equivalence point. So now, let's do a point past the equivalence point. It says determine the pH when 50 milliliters of our 0.2 NaOH has been added. So again, I'm like, well, it's yet another step in a titration calculation. Let's use our NDS setup here. So first thing I wrote, my net ionic, H plus OH yields H2O. Yet again, I'm going to do my dilutions, my two vums. For hydrogen, I originally had that 60 milliliters of 0.1 molar. Aren't we getting sick of using that same starting data over and over again for that hydrogen, right? But that's part of being the analyte, is that when it's in that Erlenmeyer flask at the bottom, I'm not changing the amount of that. I just keep on adding more and more of the titrant to it. So that's why for the analyte, that initial amount never changes. But once I put this 50 milliliters with the 60 I originally had, that's going to give me 110 milliliters. And so that's the other part of my voom here that I would want to solve my X. So that gives me a hydrogen ion concentration of 0.0545 molarity. So then I would do the same thing for the hydroxide. I started with 50 milliliters of 0.2 molar NaOH, and so I plug that information in here. I want to figure out, though, the molarity at 110 milliliters. So I solve my voom, and that gets a hydroxide ion concentration of 0.0909 molarity. But now look what's happening here. Look which one is the smaller molarity. Hydrogen now is the smaller molarity, right? So I'm going to be using all of that up. All of it's gone because I passed the equivalence point. And now because I'm still adding that NaOH into it, I'm going to have excess hydroxide remaining in there. And so since hydrogen's now the limiting, I'm going to use all that up. It's going to be 0. And so I would do my subtraction here in order to figure out how much hydroxide is remaining. So now I'm going to use the hydroxide to figure out my pH. Now I know a lot of you are thinking, oh man, Marusik, there's no calculation that gets straight from OH to pH, and that would be right. So this is one where you would have to use 2 calculations in order to finish solving this. I would need to take the negative log of my OH, my 0.0364, to get my POH, and then I can do 14 minus that to get the pH. So here the pH ends up being 12.561, which makes sense. We know it has to be somewhere above 7 because now we are, in that basic zone where I have more base than I had acid in the solution. Now let's talk about ions present. We know spectators are still in there. Sodium ions, chloride ions, they're in there. But now, out of these 2 guys, think about what's going to be left in there. I'm going to have now hydroxide ions in there. No hydrogen ions because that was the limiting and they all got used up. Whew! Now, we calculated a lot of pHs there. Here in just a moment, what we're going to do is we're going to take all that information and we're going to plot it on a titration curve. But before we do that, we have a question here. Which of the following indicators would have been best to use in this titration? If I was actually doing this in lab and I wanted to confirm all of this data and actually do the titration using a pH probe, which indicator would I want to use? Well, remember, we want to pick an indicator that is going to change colors at our equivalence point. And remember, our equivalence point for strong acid, strong base is going to be at 7. And so therefore, the best one to use here out of the 3 options given to us would have been the phenol red. Why? The phenol red's pH range of color change best matches the pH of the equivalence point for this situation. All right, last but not least down here, we're going to construct a titration curve. So the first thing I would have done is added pH to my vertical axis, and then I would add the volume of my titrant down here on my horizontal axis. So notice that I put the volume of the 0.2 molar NaOH added. Again, because that was my titrant. I always want the titrant down here. And so then what I did is I plotted some points for all of the 5 calculations we did. So this was the first calculation where we said that the original molarity was 1. This was the second calculation. After adding 10 milliliters, we ended up at 1.243. Here at 15 milliliters, we had a pH of 1.398. Then at 30 milliliters, our equivalence point, we jumped up to 7. And then at our final calculation of 50 milliliters added, that gave us that pH of 12.561. And then I would want to kind of connect the dots. But you've got to be careful. I always kind of accentuate where I know that equivalence point is at. So I kind of make it a vertical line there, and then I just kind of go and curve it out. Now, obviously, the more points you calculate, the better curve shape you could get out of this. So I'm kind of ballparking it in here. But if you did more calculations along the curve, you could get a better shaped curve, a more accurately shaped curve. All right, I hope we're feeling okay with doing these NDS calculations. net ionic dilution stoichiometry. Again, eventually we are going to do this same process for a weak strong combination. I think some of you can already see the issue that might exist with a weak strong combination. Here on these strong, we didn't have to worry about equilibrium, right? However, when we get to those weak strong ones, equilibrium is gonna come into play, and we're like, oh, great, that's gonna be fun. But we're gonna go ahead and pause here and make sure that we feel really good about doing these before we move on to those other types. All right, if you have any questions or need any help, please feel free to email me. Bye, guys.